Practicing another incline. The key to this one is the component work. We need to get components of gravity. This one, going again with another nice angle, this time 45 degrees. Means the 45 fits in down here. I'm going to draw the object just as a dot. I'm going to put it kind of close to the top of the hill. A normal force, by definition, is always perpendicular to the incline. Gravity is always straight down. I'm going to label gravity on this side. Friction in this case, judging by the numbers, since this hill is so steep, this object's going to slide downhill, so friction is going to be uphill. By definition, friction is always parallel to the incline. So at first glance, it looks like friction and normal are on a funny angle, but they're actually good. Normal's already perpendicular to the incline, friction's already parallel to the incline. The problem is gravity. Gravity's on a funny angle. So I'm going to need to find the perpendicular component. Oops, that's a little bit long. I want to redraw that. Need to find the perpendicular component and the parallel component. This side down here that I drew in red is FG parallel. That's what's pulling it downhill, fighting gravity to get it moving. And this side here in purple is FG perpendicular. So using the perpendicular sign for that. Kind of like we did before. Oh, sorry, one last thing. 45 is the bottom angle. This would also be a 45. This would also be a 45. The angle of the incline shows up in the gravity component triangle. Instead of vertical and horizontal, I'm going to call it perpendicular because it's perpendicular to the incline, and then parallel to the incline. Perpendicular. There's only two forces acting perpendicularly. The normal's pushing it off the ramp, and the component of gravity is pulling it into the ramp. The question doesn't say anything about it flying off the ramp or falling through the ramp. So this is kind of like our boring case scenario, but because we're on an incline, it's not Fn equals mg. The net force is a component of mg. In this case, it's adjacent to the angle, so that's going to be a cosine. We could crunch that out as a number. I'm going to leave it as an expression. You'll see why in a sec. Now we can jump into the parallel component. We've done questions like this before. We've got a tug of war, one force pulling it, in this case, downhill, another force pulling it uphill. The downhill is winning, so we're going to make that our positive. FG parallel, in a way, it's kind of like an F applied. It's the F applied, friction's fighting that, and that's equal to MA. FG parallel is opposite the angle, so it's mg sine 45. FF is mu times Fn, so it's mu times mg cos 45, and that's equal to MA. What's cool about these gravity questions, these incline questions, sorry, is since they're driven by gravity, we've got an m in every term so far. Well, in this case, that will change up as we go. There's enough here that we can solve for the acceleration. It's 9.8 times the sine of 45 minus the coefficient. In this case, the coefficient I made up was 0.3 times 9.8. I could have factored out those 9.8s if I really cared, but I'm just going to crank it out on a calculator, and I get that the A, by coincidence, it's 4.9, same as I had in the last question. That's just coincidental. Steeper hills should make it go faster, but this time I added friction, which slowed it down. So same method. This time we had to do the perpendicular to get the normal force. It's a cosine relationship. And then we had a tug of war in the plane of the hill. The component of gravity minus friction was equal to MA. And then just work it